Hi, this is Mark Weitzman. Welcome back to our series of videos on final problem 4, complex analysis from the Russian MOOC on complex analysis. So we've established this pole structure and branch point structure. Now, in complex analysis, you can deform contours, but you cannot cross a pole and you cannot cross a branch point. You can cross a branch cut, but you can't cross a branch point or a pole. So, as I mentioned earlier, there's an easy way to solve this problem. Actually, there's two easy ways to solve this problem. One involves residues at infinity, but that takes some visualization, which is currently beyond my powers. But there is an easy way to solve this by closing on this circle, and I'll do that in a couple of videos. Right now I'm going to proceed with the hard one, and what I'm going to do is I'm going to deform the contour. Because these poles are not near the contour on the respective sheets, I can deform the contour. So let's do that. So now what I'm going to do is I'm going to take our contour and I'm going to go straight into the origin, basically on this branch line. I don't have to worry about this pole here because it's on the other sheet. I'm then going to go from the origin straight to the branch point. I'm going to go right around the branch point and then go back on top, basically to the origin again. Oops. We use dotted lines to indicate that we're continuing the function analytically on another sheet. So here, and then we're going to go straight to here, to infinity. Okay, so this is our new contour, which we can calculate. And what I'm going to do, I promised you a little while ago in the first video that we should first make sure that these divergences cancel. So I'm going to divide this up into 6 integrals. I'm going to call this part from infinity to here, I'm going to call this I0. I'm going to call from here to here, and we'll see that these all have essentially the same value within like a imaginary number, complex conjugation. I0, I1, I2. By the way, there's a little circular piece here. You might think that adds something, but it doesn't because it's infinitesimal. And if you look at the function f at z equal 1, it's perfectly well behaved. This is 0. That's from the branch point, but we have a -1 here. So there's no pole or anything to worry about. So don't worry about this little circular arc here. I'm going to call this I3. Remember, we're proceeding in this direction. Boom, 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 boom. I'm going to call this portion here I4, and then this out to infinity I5. So we got 6 integrals, but like I said, it will turn out that this one cancels this one, and the sum of these are basically, two of these are complex conjugate pairs, and when we add them, we'll take the imaginary part. We'll only have to evaluate one integral, as you'll see. So let me start showing that the divergences cancel. So let's do the I0 integral. First of all, on this integral, z is equal to rho e to the minus 2 pi I over 3. So dz is equal to d rho e to the minus 2 pi I over 3. So I0 is equal to the integral from infinity to 1, because this branch point is located all the branch points are on the unit circle, one away. D rho times E minus 2 pi I over 3 divided by, now remember on sheet 1 this is I0. Okay, so now I have to look at the phases a little different. We know that the starting phase is minus 1 times e to the minus 2 pi I over 3. We established that a long time ago. The poles over here, I didn't draw them in there, but these points inside here all have a phase change that we calculated. But now we're outside the branch point. And it's easy to see that outside the branch point on this line, there's no phase change. Because if I calculate from like here to here, you're going to go boom, with that arrow, and then it's going to go boom with that arrow, and there's no change when you do it exactly. So there's no change in the branch point, no phase change from this branch point, and the phase changes from this branch point as we come in, they're equal and opposite, so they cancel. You can calculate and verify this. So there's no phase change on this branch point. We're just left with the starting thing. So I have minus 1 e to the minus 2 pi I over 3 rho cubed minus 1 to the 1/3. Whenever I have this, I always mean the real function. That's why I'm not writing it as absolute value 1 minus rho cubed to the 1/3. This is positive anyway, so minus rho, minus rho e to the minus 2 pi I over 3. And this simplifies, change the limits, gives us a minus sign, which cancels both these minus signs. So we end up getting the integral from 1 to infinity d rho. And notice we have the same phases at each point. So we get d rho, rho cubed minus 1 to the 1/3 plus rho. So that's our first integral for I0. Now I want to do I5. On I5, z is equal to rho e to the minus 2 pi plus 2 pi I over 3. So dz is equal to d rho e to the 2 pi I over 3. And what we really need to figure out now is the phase change on this portion of the integral. And it's not too hard to calculate, and it's kind of what you'd expect, but I'm just going to write down the answer. That imagine you were very far away. It holds all the way into 1. It holds all the way into here, but imagine you were very far away. Then clearly, for this branch point, you went from there all the way to there, and you followed on this contour here. So basically, you rotated, let's show, from that branch point, you rotated all the way like that. So this is 4 pi I over 3. 4 pi over 3 for the phase that you rotated from this branch point. And from the branch point over here, you basically see you did the same thing. It's different, but it works out that any slight differences, at infinity you could see it very easily, but here it's not so easy to see, but they all cancel in. So you get 4 pi I over 3. And then the same thing on this one. You go from here all the way. So the total phase change is 4 pi over 3 times 3. And then for the h function, we divide by 3. So we end up getting 4 pi over 3. For every point on this thing outside the branch point, on the branch line, over for I5, it's 4 pi over 3. So to calculate the integral for I5, I'm lazy here. First of all, we're now going from 1 to infinity. This is now a plus sign over here. And now we add I got to add another phase here, e to the 4 pi I over 3. And this is a plus sign. So now our integral, our I5 is, this is I1. I'm sorry, this is I0. Now I5 is equal to the integral from 1 to infinity. I'm going to get 2 minus signs, so now I'm going to get a minus d rho. And notice this times this is e to the 2 pi I over 3, e to the 2 pi I over 3, e to the 2 pi I over 3. So everything cancels, and we get rho cubed minus 1 to the 1/3 plus rho. So you can see that I0 and I5 are the exact opposites. If we go out to the same distance here, we're going to get an exact cancellation. So that is our conclusion. This asymptotics I0 plus I5 equals 0. We don't have to worry about any divergences. And now we have 4 more integrals to evaluate: I1, I2, I3, and I4. I'll write them down, and I'll show that they combine all into one integral in the next video. Thank you very much.